All right, one quick note, which I think I wasn't quite clear on last time. So if you are in the A section, you have to be here in class, right? That's actually required, and part of the class comes from quizzes, which we'll get to in a second, or in-class polls, sorry, which we'll get into a second. If you're in the B section, for now, I said you could come to the last lecture. For now, until for the next about probably 2 weeks, I'm guessing, make an effort not to come to class if you're in the B section only. Otherwise, we have this every time. Now, I promise you it will clear out a little bit by the time, and everyone that wants to come can. Most people taking the B section actually would prefer to watch them at home, I think. But for now, we're not going to check. It's all on the honor system, but don't show up unless you are in the A section, or it could get pretty. It can get like this every time, and that's not great. First lecture is okay, but this is getting a little can't have this every single time. So if you are in the B section, remember your class participation will be through the quizzes after lecture, and if you're in the A section, participation is through the in-class polls. I guess this is actually the announcements I had here. Class attendance is required for the A section. If you are in the A section and would rather be in the B section, just switch to the B. And you want to watch remotely, just switch to the B section. That lets everyone that wants to come to class come to class. It really, despite appearances, it really will filter out within about 2 weeks or so. So it should be fine, and people can come. But until we reach that point, I'll make a post on Piazza when we reach that point. If you're in the B section, do watch the lecture videos at home. Don't come to class. And it's the B section, or really anyone that is watching the lecture videos at home has to fill out the quiz, or the B section has to fill out the quiz if they're watching it at home, and the B students don't need to do the in-class polls, and the in-class students don't need to do the quizzes after lecture. So sorry, it's a little bit confusing. There's no, unfortunately, 400 person lecture hall here, so we can't do anything but that. Yeah. Yeah, so that was actually in the slides last time, but it's within a week of the lecture being posted. Yeah, so the Section B students, within a week, watch the video, fill out the quiz online. Okay, so today's lecture is on data collection and scraping. And this is actually kind of a little bit out of place lecture in that we kind of jump right into one topic before introducing things like Python or Jupyter Notebook. That's sort of intentional. I kind of want to jump in to see a little bit about the kind of content we're going to cover in the class. And then next lecture, we'll kind of take a step back and have more of a lab on Jupyter Notebook and some basic features of Python that you'll be using throughout this course. So if some of this code looks a little bit fast, come to the next lecture. You can sort of follow along in the Python notebook that we're going to use, and hopefully it'll be a little bit more obvious. Okay, so there's three main things I'm going to talk about today. First of all, data collection process, how we go about getting data from different sources. As you might imagine, the first step of data science is to get some data. Then I'll talk about some common data formats. And this is sort of, again, somewhat just sort of bookkeeping, but it's really important to know some of these things. These things come up all the time. We'll particularly talk about CSV files. We'll talk about JSON objects, and we'll talk about XML objects. And then I'll finally talk about regular expressions and a little bit about parsing at the end of class. Okay? All right. Assume no questions. There's no technical questions yet. If you have sort of logistic questions, either quickly now or we can talk on Piazza. We're hopefully responding fairly quickly on Piazza to all the questions we have. All right, so let's just jump right into data collection. Okay, so as you might imagine, the first step of data science oftentimes is getting some data. And you'll typically get data, as data scientists, you'll typically get data in a few different ways. You'll either just, someone will give you a file directly, right? Someone will just email you a CSV file and say, hey, analyze this, or a bunch of CSV files maybe and say, hey, analyze this. You might query data from a database, right? That's actually very common. There's some database that stores all the information. You have to write a set of queries that actually get that data and put it in the form you care about. You may query an API. So there's a lot of web-based APIs that you use. Well, these days they're usually web-based. They in the past have used other things. But something like a web-based API, you'll query. And then finally, you might do things like scrape data from a web page. And these have different sort of levels of sophistication too, right? There's different levels of which you need to kind of specialize the data to your, specialize the collection process to your task. But we'll cover some of these today. So there's not much to say about getting it from a file, right? Someone gives you a file. We'll talk a little bit about data formats in a second. But there's not much you have to do to get the data. Querying from a database is hugely important, and we will cover this much more in a later lecture. We'll cover relational databases and relational logic I say that in the highest level possible. We'll cover the very, very basics of relational databases and kind of the concepts behind them. But we'll cover that in a later lecture. It's worth a full lecture sort of to cover that. It's sort of very important stuff. And today we'll talk about these two. So we'll talk about how you do things like query an API. So if you use some service that has a, for example, REST API, we'll learn a little bit about how to do that. And then later on, we'll learn how to scrape data from a web page today. Now, as I said, this is all sort of in the data collection phase of things, right? So going back to the big picture of the class, we're talking about first data collection, data processing and data collection, then kind of data analysis, and finally more the debugging process. But this is kind of the nuts and bolts of what you have to do to kind of get data and get some raw materials to work with. So let's just jump right in. The first sort of step of web-based data collection, and I will focus now on collecting data from the web, is to use HTTP requests. And at least HTTP, which stands for Hypertext Transfer Protocol, you don't need to know about that. It's just the little thing that goes in front of web addresses you see, is how you get data from web pages and web APIs. And so now I sort of did promise that in general we're going to look under the hood of different algorithms, right? So I won't just teach you how to use scikit-learn. I'll teach you actually a little bit about how to implement a machine learning algorithm. Here I'm taking a step back from that though. I will not teach you how to implement an HTTP protocol because you have to stop somewhere, right? I mean, you can take a networking class if you really want to know that. And so what you should do instead is the following. So if you want to get data from some web page, say I want to get data from my data science course web page, we'll use a Python library called requests. And I'm actually just showing this to you here for a particular reason, which I'll talk about in a second. But we're using a library called the request library. It's at this URL if you want to go look for it. And the way you call that in Python is you import the request library. You call request.get the web page, and then the status code says, like, I think it's 200 if you get it right, if it's a good URL. Otherwise, it's 404. The content actually has the website text. There's some headers and content type, etc. And you can actually run all this code and see what it executes. Now, very important here. I'm putting code like this up on the slides. And I'm going to do this a lot during class, kind of put a block of code. And I'll kind of go through what it does. It's very important that you understand that I'm not telling you to memorize these function calls here. So do not write down, OK, there's request.get. And I have to learn that call, right? So with all these things, what's really important is not to know specific APIs, specific libraries, but to know how to actually go about getting that if you really want to, right? So how do I actually go about downloading a web page if I really wanted to, okay? And the way you do that is not by memorizing this. The way you do that is you type into Google Python download web page or something like this, right? And the first hit that will come up is usually a Stack Overflow page that will have a link somewhere to the request library. And you follow that link, you read the documentation there, or I really use this is usually the first example here, and then, or not with this with this page, but something like this will be on the front page, and you actually just sort of use that code. Okay, so really one of the main lessons of this class is that I'm going to sort of demonstrate bits of stuff that you do to get something accomplished, like downloading a web page, but really it's just an example. What you should really learn how to do and sort of take away as I discuss these things is not to do this exact same thing, but how to go about the process of actually finding a web page if that was or downloading a web page if that was something you wanted to do. Okay. Now, having said that, I will talk a little bit about sort of this library and how you use this library to query URLs. But don't worry too much about the details here, because all of this can be looked up. And I'm using it as an example, something to walk through that you can then sort of use on your own and figure out from the documentation on your own as well. The number one sort of skill of a data scientist is not knowing libraries, it's knowing how to find the library you want for your particular task. All right, so this makes sense to everyone, though, how I go about sort of querying a web page, assuming now, jumping back into the details here and saying this is how I actually get my data. So this will return data that looks really nasty. It's HTML data, which we'll actually talk about parsing later in this lecture. But these are sort of the different parts that you get when you actually query a web page. Now, I do want to include a few basics of these things because these things are important enough that they will come up again and again. And there are sort of really two important parts, I think, to web-based queries. The first one is parameters to URLs. So we've all seen URLs, right, where they sort of says, like when you do a Google search, right, it says /URL, and then there's a bunch of sort of nonsense after that, where it is some thing like SA equals T. So there's a bunch of sort of assignments separated by ampersands. And those are called parameters to a URL. And the way you will use them in a library like requests is that you fill out a Python dictionary with all these parameter assignments, right? So if my URL, this is actually probably a bad one. I think Q here is the query, but I don't even know what I'm querying in that one. Maybe nothing. That's my Google homepage. So if I query something in Google, I would specify a term in the Q parameter, right? And essentially, the reason why I do that, I mean, there's a lot sort of goes on behind the scenes here. But basically, what's nice about the request library is that you can just fill out a Python dictionary with all your URL parameters, call the request.get with params equal your parameters, and that will return the web page or other whatever HTTP call you make with those parameters assigned to the call. Okay. Now there are other HTTP. This is sort of the HTTP GET request, which is usually used for getting data from a website. If you are posting data to a website, if you are filling out some form and actually issuing some update to the website, you'll use other methods like the post method or the put method. So these are all parts of the HTTP protocol. And it's important enough, and you see it enough, that it's worth covering very briefly. But like I say, the important thing to realize is that this is sort of how you go about requesting and setting data in a website. And I have to sort of start with this, but I'll talk shortly about what we actually do with the data once we get it, or how we go about posting more data. Okay, any questions so far? Okay, so let's keep marching right along. The next thing that you may see in sort of the data science world, which is also web-based, but it's a little bit more complex, are called REST APIs. REST stands for Representational State Transfer, but no one actually uses that terminology anymore. It's just a REST API, right? And so REST is actually not really, it's sort of calling it an API is sort of a misnomer. It's more of a design architecture, really. What REST APIs do is they are essentially, there's a few key points to them. Essentially, they are a way of issuing requests to a web page and getting responses back from it. And we'll see one in a second. So obviously, the return data from the previous call would just be a big a big HTML page that contains the raw data of a website. REST APIs oftentimes return a little bit more structured data. But the important point is really two things. The first part is that it uses standard HTTP to issue its queries. So if I have, and I'll talk about the GitHub REST API in a second, if I want to issue a query about sort of my GitHub account or issue queries about other GitHub repositories, things like that, I use HTTP to do it, but I'm not actually getting a web page back, right? I'm actually issuing a request to an API and I'm getting information back, usually in some pretty structured format. And the big deal, or the big key point to REST actually, is that it's stateless. So this is a sort of a subtle point, but it's also an important point to sort of think about when you're using these APIs. What this means is that the server doesn't remember anything about you when you're issuing calls to this API. Okay, and what that means is that there's no like login procedure or anything like this where you start a session and then I can keep downloading things from that session like there are really in most other APIs. Part of what was so great about REST and why it's become so popular is that it's so simple because every single query you make kind of starts something brand new from the beginning, right? So all of a sudden from the beginning again, you're actually saying what your account ID is. Here's my account ID, here's the file I want, here's the information I want. It sends it back to you, and then it forgets about you entirely, right? It doesn't remember that you made that query, doesn't remember sort of that you logged in before. It's just giving you that query. So let's look at a quick example here. We looked at an example before of sort of an HTTP normal request. Here's querying a REST API. So the query REST API, it's similar to most HTTP requests, but you'll almost always need to include parameters, right? Because you have to at the very least, tell it your account information or your account name or what information you want, or it can't really return very much to you. All right, so here's an example of querying a REST API for GitHub. So GitHub, I assume most people here know what GitHub is. It's a repository, or it's a system for building repositories in Git. Actually, all our course material is stored on Git, or on GitHub. But if you want to use the GitHub REST API, you need a few things. So the first thing you need to do is you need to get an access token. All right? And because there's no login information on GitHub, or on the GitHub REST API, what this means is that there's no way for it to sort of know who you are, right? And there's no way to know that you're your user instead of someone else. Okay? And so because of that, we need to somehow have a way of effectively authenticating ourselves when we issue our query, so that it knows, if I say I want to give you, tell me information about myself, it knows who the myself is, right? It knows to give me information about my username and not someone else's. So the way you do that, and this is actually kind of a technique you'll go through a lot if you use a lot of REST APIs, is you'll go onto some online forum, logged into your account, and you'll get a token. And this token actually both corresponds to whatever particular account, whatever particular task you're trying to do usually, as well as your account. So I'll get a big long token string here. I actually should have put it in there because I've since deleted it, but it'll be in the notes that I post shortly. You fill out the token, you say request.get, api.github.com/user. The /user is an API call, which gets you information about the user. So in this case, it'll give me information about my GitHub account. And then as a parameter, you pass the access token equals this token that I've gotten from my website here. Okay, so again, the high-level point here is that what we're doing is we're getting information about our account. And I'll show you what this returns in a second. Where's that? No, I don't. I should do that. It's on. Oh no. Okay, here it is. Right. It returns things like this. It returns an object that sort of says my login name is Z Coulter, my ID is this, my avatar URL is what. I don't think I have an avatar URL in GitHub, but it gives me a URL for it anyway. The point is, this is sort of an example of how to use GitHub API to actually query data, right? And as there's a lot of websites will sort of offer REST APIs to query things that you want about them, and they can be very handy because they're sort of so easy to manage. They usually do return data as what's called a JSON string, which we'll get to in a second. It's sort of a nice format for sort of quickly storing a lot of different information about URL, about strings, numbers, IDs, things stuff like this. But we'll get to all that in a second. And remember, the example here is that the server does not remember your last queries, so you always need to include your access token if you do it again. Okay. All right, now just to finish this, because again, this is sort of the brief stuff, but you have to do this if you're going to get any data from a website. The last thing I'll talk about is authentication, which is there's a couple ways of doing this. I can actually also use GitHub's API with what's called basic authentication, and that's done by passing an auth argument to the request.get function. And that includes, often includes my username and my password, which is not password. I've just I've deleted my actual password from that. Now, this is called basic authentication, and this is actually kind of, it's similar to a REST API in that every time I make a call, I am re-authenticating myself, right? I'm passing my authentication every single time I make any call, and that kind of can also work. Now, most APIs at this point have replaced this basic authentication with some form of what's called OAuth, and you'll play with that a little bit in your homework, and you sort of get familiar with that and figure out how to use that. But really, to a first approximation, I think this covers almost all you need to know about scraping data from web pages. Sorry, not scraping, but issuing the basic calls to web pages. You're probably going to interact either with just normal pages, which are going to have URL parameters, or you're going to interact with REST APIs, which are sort of called like this. So that's sort of the basics there. And with that a little bit out of the way, I want to jump into the actual formats of data that you might find. But are there any questions first? Yeah.
Could you explain the params?
Sure. Yeah.
So I see there's a key value, and then there's
Yeah, so I don't want to explain what those are because I don't actually even know what those particular things are. Those are just parameters. That was more of an example. I copied a URL from Google and sort of said, you've seen these URLs with all these sort of ampersands and equal signs and these kind of things before. Those are just an encoding of queries like that. So normally, and really, this is probably a better example here. In the GitHub API, I need to pass a parameter called access token, which is my token. So the way I do that is I create a dictionary, a Python dictionary, with the key access token and the value of token, and I call the request.get call with that as my params value, and that issues the URL query. It's essentially the same as putting /user ? Access token equals whatever my token is. That would be the same thing as doing that. And the nice thing about requests is that it handles all these things like escaping white space and stuff like that, because you can't have spaces in URLs. So if you've ever seen like the %20, that's the replacement for a space and these kind of things. Requests will handle all that for you. So you don't have to worry about that. It'll just kind of do that for you. But don't worry about this one. The one before was just an example of there being some parameters in that URL. Yeah? No. So usually you have a token, which is, well, actually here, okay, in basic auth you mean? No, this is actually HTTPS, so it won't be transferring it in plain text. There actually will be some encoding in addition to just the HTTPS, but the HTTPS is what you want to use when you use authentication like this. As I say, it's mainly moved away from this to OAuth, which is a more complex system that actually doesn't quite matter as much if you transmit some things over plain text, so it's not as big a deal, but this is sort of why people don't want to do that. But no, you're not just transmitting your stuff over plain text. No, it's encrypted. The URL request is, and the password information is encrypted within that request. Yeah. Yeah. Yeah, so actually everyone has an account can request multiple ones. You don't have one by default, but if you go to that page with a GitHub account, you can request a token and it'll generate one for some purpose. You can actually make multiple ones, so I can use different ones for different applications, for example. And you can also, delete them, and maybe you're not supposed to share them, but you could share them. If you want to give someone very limited access without giving them your password, you could actually do that and give them sort of limited access to certain calls. So there is sort of a whole, there's kind of a whole authentication system within that, but for the most part, that's up to the different API creators, so they can do it as they sort of see fit. Okay, so let's keep going. Let's talk about common data formats and handling. Okay, so once you've gotten some data, and this actually applies, I would say, equally well to the case where you've queried data from a web page or you've just gotten a file handed to you. There really are three formats that are by far the most common to encounter in data science. I guess there's certainly other types of formats people use for data, but these really somehow do really make up the core of what you actually encounter 90% of the time in practice. If people have other thoughts about what might you want to include in here, I'd be interested to hear, but this seems to be about the extent of it. The first thing are comma-separated value files, are CSV files. It's actually a misnomer because they're not separated by commas, they're just separated by something. The next one is JSON files. JSON stands for JavaScript Object Notation, and they really are a nice way of transferring data as a file or even as just a string, at least simple forms of data. And then finally, things like HTML or XML. HTML is really, it's unfortunately not a type of XML. It's sort of a kind of messed up cousin of XML that has no real rules to it, so it's sort of a total pain to actually deal with in practice. But HTML is the language of the web. It's the hypertext markup language. It's what websites are written in, or at least what they are displayed in your browser in. And so if there's no API for what you want, but the data you have is somewhere on a website, you may just have to query it in raw HTML and then extract the actual content from that page, which we'll talk about how to do in a second. But this really does seem to be kind of the most common types of data formats. Now, for particular applications, of course, there are other ones. So if you're working with relational databases, there's a whole set of formats you use for relational database, but you'll almost never actually interact with that format itself. You just use the calls of the relational database itself. Similarly, if you're working with like geographic systems, there's a whole set of file formats that deal with geographic information systems, but you'll never edit them directly or interact with them directly yourself. It almost doesn't matter how they're stored internally. But these ones sort of kind of does matter how you store them internally. You should be enough familiar with these things that you know how to access these files and know how to write them and sort of know how to process them. So this is why I include these three ones here. Okay, so let's just jump right in. CSV files. As I said, CSV is a really kind of a bad name because it stands for comma separated values. And so here's an example of a CSV file that I can actually download from the S3 page, not the Amazon S3, but the S3 CMU's course management system, giving me my roster of a class, right? So this is not my actual roster, because this is me in the class, but I don't want to share the whole roster with everyone. So if I can download a roster. This is actually the last offering of the course. Download some roster for the class, and these things come in the form of a CSV file. In fact, a lot of times, various web pages, when you download some data, they'll just let you download it as a CSV file. And the lines in this look like this. So the first line in a CSV, so every line in a CSV file is delimited by some delimiter. So the different values are sort of indexed by some delimiter. In this case, it is a comma. So they're separated by commas here. And so the first value is semester, then course, then section, etc. Now, in the first line of most CSV files is a header file, or a header line. So that actually indicates what each column is. And subsequent lines then are value lines. So this sort of indicates value. Now, there has to be the same number of rows in each, of columns in each line, or it's considered kind of an invalid file. So there actually are the exact same number of commas in the top one as there are in this one here. But hopefully it's pretty apparent what this is doing, right? As ugly as it is to actually just read like that in one big text file, it seems kind of obvious what it's doing. So the first line sort of gives a bunch of different column names, and then the next line gives you the actual values that occur in that row. So the semester is F16 in this case. The course was 688. The section was the B section. So I was taking the online only section last time apparently. Lecture, it is a lecture, and then my last name, first name, my Andrew ID at some point, no middle initial, but Andrew ID, email, etc. Right? So it sort of makes sense, right? You can kind of handle this pretty well. And they're sort of very easy to work with too, right? Because the reason why they're so popular, by the way, is just they're so obvious what's happening here. You can look at it, you can inspect it kind of visually in text. It's not always that nice because you can't quite correlate and say what column is that. I don't really know, but fairly easy to sort of inspect visually. Now, one issue that might come up is what if the values themselves have commas in them, right? So the commas separate successive lines, but what if a value actually has a comma in it? What do you do then? And that's why you actually also have something called a quote character. So anything inside of two of the quote characters is considered value, even if it has the delimiter in it. So in this case, the quote character is a quote, double quote. And I don't think there are actually any commas in any of the values there, but there could be, and it wouldn't be a big deal because a comma inside quotes is actually not considered a comma. Now, you actually don't need quotes around things that don't have commas in them, because if they don't have a comma, then they're clearly just one field. But it's pretty common just to add commas around, or add quotes around every field that you sort of want, just for the sake of it. Now, you could sort of pretty easily, I think, in Python, kind of write from scratch a parser for CSV files, right? You sort of look for all the occurrences of the separator character, the delimiter character. If you maintain a quote character, you wait until you find another one before you sort of close that. Everything in between is values. So it's sort of kind of apparent how you would actually go about writing a parser for this. But we're not going to do that. You are going to write a parser in 688 for more complex formats, but not this one. For CSV files, the most common thing to use is just the pandas library. So we're going to use pandas a whole lot in this class. It's a very common library for dealing with tabular data, also doing some basic kind of analysis with this data, and doing very basic relational database-like structures. It's kind of a grab bag of doing a lot of different things, but it ends up working quite well. It's sort of a library that really lets you do a lot very quickly with data. It's sort of it's a general purpose kind of tool for data scientists to manage data. We'll talk about it a lot more later, but the one thing that I'll say so far is that this is one call you might actually want to memorize. It's just read CSV. It's not that hard to remember. Is sort of what we'll use to parse and process CSV files here. So that's all I'm actually going to say about CSV files. They're, despite being so simple, they actually probably are the most common way I ever saw data given to us in industry as a data scientist. Everyone loves CSV files because there's no way to get it kind of wrong. I should say that I actually mainly saw ones that were not common delimited. There were other delimiters, but your mileage may vary in that respect. Okay, so let's move on to a little bit more interesting thing, which are JSON objects, or JSON strings. So JSON files or JSON strings, a file will just contain a big long string of JSON, was originally kind of developed as a way of encapsulating JavaScript objects. So it was originally developed as a way to sort of transfer objects in JavaScript to serialize them and transfer them between, write them to disk or load them from disk, etc. And JSON can really store 5 types of things and 5 types of things only. There really doesn't get any more than this. There's 5 different data types that it knows about. It knows about numbers. So 1.0 is a number. It's always kind of assumed, you could leave out the 0.0, but they're kind of always assumed to be floating point. Even if they don't have, there's no distinction between integer types or floating point types in JSON. It's just numbers, right? And they can have decimal places if you want. A string is just a string enclosed in double quotes, actually only double quotes, not single quotes. Any number of characters inside a string, inside double quotes, is a string. Booleans, true or false, those just 2 characters. Actually also null, I think, N-U-L-L is, I didn't put there, but it's also a valid JSON string. It means the same as false, basically. And then the interesting ones, which are lists and dictionaries. So lists are called arrays. They're actually called arrays in JavaScript. Dictionaries are what we call them in Python, but they're really called objects in JavaScript. A list is enclosed in brackets here, and it consists of some number of items that are common delimited. And a dictionary is surrounded in brackets there, where the keys are strings and the values are something else. Where here, any of the items or the value here can be any other JSON object. And yes, of course, you can make things hierarchical. You can embed them. So you can have a key. The key is a string, of course, but then the value for that key is something like a list. The lists can have sublists in them. These can all have sub-dictionaries in them. They can have values that are numbers or whatever. But it's a really kind of basic and simple formula for creating data storage. And it's gotten incredibly popular recently. I think much more so than any other kind of format for storing things like that. I think formats like XML, which we'll talk about in a second, were kind of thought to be more general and thought to be more useful, but they've really been almost replaced by JSON in a lot of cases, if you don't need the full structure of XML, because this is just so easy to parse. So here's some example data. This is actually the result that I get if I query my GitHub API, the REST API. And as you sort of might imagine, most REST APIs, or as you saw maybe, most REST APIs return something in JSON form. They don't have to, by the way. They can return whatever type of data you want. But it's extremely common to get data back in JSON when you make REST API queries. So you'll get sort of used to seeing these kind of APIs here, or these kind of results from queries you make. Any questions about this? Yeah.
The request that was like it has that JSON, but is when
So are you talking about the fact that the
They usually return JSON, right?
yes?
When they don't, just
Yeah. So any API call will return, any requests.get call will return some content. If you query a web page, it'll return probably HTML. If you query a REST API, it will usually return JSON, but it could actually be anything. It could be XML. It could be HTML. It could be really anything. It could just be raw text or images, right? Actually, it could be really any format. And I didn't really highlight it here. Again, this is sort of the things you end up looking up in documentation. But if I go back for a second, the response.headers content type indicates what type of data it is. And this will actually say that it's JSON data or HTML data or anything else. And you can use that to figure out what it actually is. Now, almost always, you'll sort of know what it's returning to you before you actually issue the query, and so you don't have to worry about that. But you can, if you need to, kind of figure out what data type programmatically you're actually getting back. Yeah. A connection object? No. So that's sort of the nice thing. The question was, do we have to have some sort of connection object, something like that? So the nice thing is that no. The nice thing about REST APIs is there's no notion of a stateful connection. You just constantly issue queries that return results, just like you would with a web page, right? There's no notion of a stateful connection really in a web page. There is, at the TCP level or whatever, but that's not something we kind of care about here. Every time you want a new piece of information, you just issue a brand new request, include all your information that you want, and then go from there. Usually, if there is some sort of state you're exchanging, the state will be returned by one call, and you'll pass that kind of identifier of state to your next call. So every time you make a call, you have to sort of maintain everything you need to capture whatever your current connection sort of status is. But really, there's no notion of a separate kind of connection in these REST APIs.
So it's like I get a connection object in response, and I have this field, so I store them, and again I do another response that get send whatever I need.
No, so once you have your response, sorry, the question was, I think, and what you're probably thinking about is that different libraries do encapsulate this different ways. In the requests library, I think the question was whether you do response.something. You never call response.get. Response is just a returned object. It's not a library. You always call request.get to get your information. The response is just a static returned object then. It's not something you ever use as part of a connection or anything like that.
But the fields can be used to make another request.
Yeah, so the fields you can then use elements of your response, like your response.content or something like that. You could parse the JSON from the request.content, response.content, and use that to issue another separate request.get call, but you never sort of directly treat the response as some kind of connection. Yeah. Unlike a lot of network code, by the way. Most network code, you sort of issue a connection, and then you issue calls and responses from this connection. You don't do that here with REST APIs. That's actually the important part about them, is that you're not doing that. Okay, where were we? Okay, so parsing JSON in Python. Fortunately, it's really easy. There's a library called JSON as part of the Python standard library, and you can just pass in a JSON string or a JSON file into JSON.loads. Load is load string. This is now a string I'm passing to it. I pass that, and I get back a Python dictionary that describes what I just queried. So for example, if I have this as my JSON that I get back, I would have a Python dictionary where these are my keys, and these are the values of those keys. And we'll talk more about Python dictionaries in a second. As I said, this is kind of a little bit jumping ahead, but we'll come back to a little bit more of a review of Python and the Jupyter Notebook next time. It turns out that they actually don't even need to go this far. There's actually even a response. The response has a function called .json, which you can call to sort of wrap this, but this is pretty easy. You can kind of do this quite easily. You can load things from a file too. You can dump an object to a string. You can dump an object to a file too. If you try to dump a JSON or a Python object that has types that are not either numbers, strings, true, false, or lists or dictionaries within those, it will throw an error, right? So if you have some new other type, like like response or something like that. So if I tried to JSON.dump response, that would throw an error. So I don't. You are very limited in what you can do. There's definitely not a one-to-one mapping between the types that Python can represent and JSON types. But anything that you can represent in JSON, you can load into Python. But just there's lots of Python you can't then dump to JSON. Okay. Any other questions?
I didn't get the object variable.
Oh, object is, sorry, object is just some Python object here. And I'm calling, if I want to generate a JSON representation of that object, I would call just dump s object. I should mention, so I'm already sort of doing my my promised thing and not having the notes out before class. Actually, the notes are done this time. I just don't have my converter to Markdown quite finished yet. So today I'll post some notes for this, and there's a few more examples that go through these things, and hopefully it'll be clear from that as well. Okay, so the last thing we'll talk about is the last sort of data format you may encounter are XML or HTML files. Now this is the main format for the web, though, as I said, XML seems to be kind of losing a little bit to JSON for simple APIs, right? It used to be that every API would return an XML object because that was sort of the standard for data encapsulation. Now most APIs return JSON strings because this is so much easier. Parsing XML actually is kind of a pain, and parsing JSON is much easier. So XML and HTML to a lesser degree, but I'll talk about HTML in a second, contains hierarchical content delineated by tags. Tags are encapsulated in brackets. There's two brackets and then the tag name and a closing bracket. Open less than sign, tag name, greater than sign for the tag name, and then the closing tag has a slash before the tag name. If you've ever worked with HTML or websites, this will probably be pretty familiar to you. You can have attributes in the tags. So after the tag name, you can have a space, an attribute name, and then the value the attribute takes. This is always, the attribute name is just text with no quotes, equals, and a value in quotes. XML is then organized hierarchically. So after you have the main tag, you have kind of subtags. The content inside a tag is everything within that tag. And then if you have a tag that only has attributes but no content, you can have a sort of an open slash close tag, which ends in a slash greater than sign. So it actually isn't too important, the details here. But what I will say is that just like JSON, there are very nice libraries for parsing XML within Python. So you will typically not do it yourself. However, for the first homework assignment for 688, you're actually going to write an XML parser, mainly because it kind of gets you very familiar with the kind of stuff you need to do to process structured data objects, right? I don't want anyone to use their own XML parser here, but writing an XML parser actually does get you pretty familiar with what you need to do to write, to process and handle data in a variety of ways. HTML, which is the web version of XML for hypertext markup language, looks like XML, but it's horrible. The reason why it's horrible is that it has no actual structure. So you can have things like open tags that never have close tags. You have to somehow figure out from this where the actual close tag is implied. HTML was developed kind of fundamentally just to show information visually from the web. And so because of this, it kind of evolved to do what people really do in practice, not to be a rigorous kind of well-typed data format. And so there are really, really nasty things that happen in HTML that should never happen in real well-formed XML. And so don't even try to write your own HTML parser because it will be a complete disaster and mess. There are a few questions here. Yeah.
So some XML files has colons and namespaces.
Some has colons and namespaces. Yeah, we're not going to worry about things like namespaces at all. Namespaces are sort of an additional thing you can add to XML tags that sort of specify kind of a meta delineator for that tag. I'm not going to worry about, you won't have to do that in your parser, for example, and I'm not going to worry about that here. It's also useful oftentimes for validating the XML. You have to make sure that only certain forms are valid, and you can use namespaces, I believe, to help validate it. But I'm not going to worry about namespaces at all, at least for our purpose. Most data formats you have, you can kind of think of namespaces, they have colons after the tag and stuff like that, is just basically longer tags. It isn't actually awful to think about like that, and just let the namespace kind of be part of the tag in some sense. All right, so the Python library we'll use, I think actually this was I had a new example from this year. This is the example from last year, but the new example will be in, I thought that copied it over, guess not. New example will be in the notes. I'll maybe copy over in the text too. This actually will not work because this was from the website last year, but I guess I could just do this really fast here. Let me just do this. If you want to find out what the lectures were last year, that's the website for last year's. So you can find out, you can parse that. But there are a number of XML parsers for Python, but a nice one that I sort of really like is called Beautiful Soup. Again, it's just one library, just like Request is one library for querying URLs, but it's sort of a nice one. And this is sort of the syntax for doing it. You import Beautiful Soup, you can import requests. I issue a request for a website, and then I say that root Beautiful Soup I create a Beautiful Soup object on the content, the HTML content that's returned for that web page. And what's really nice here is I can actually walk through this very sort of potentially very massive tree of opening tags and closing tags and all those kind of things, and I can do it in a very sort of nice way. So this is, again, applies to the HTML from the old site. I have another example in the notes on actually parsing some data from the CMU homepage. But there's calls like find, which will find a section tag with the attribute ID set to equal schedule. And then within that, I can find the tables. I can find the table body, and I can find all the links in that. And that will actually return a list of all the links that are inside table body tags, inside table tags, inside a section tag with the ID attribute, right? Sorry, with the attribute ID equal to schedule. So you can chain these things sort of very easily. And the nice thing here is that actually it nicely searches the entire hierarchy. So even if the root does not have a section tag immediately following it, it can be a few sections down, encapsulated in whatever other sort of tags you care about. It'll sort of zoom in right to this one, find it, and then be able to parse from there. So there'll be a few more examples in the notes, and I would also just sort of, in the homework, you will get a little bit familiar with it. That's the 688 homework before you write your own parser, and so you can kind of figure out how to go about using things like Beautiful Soup. Yeah. Oh, that's a good question. It's backslash, right? The backslash actually is when a Python line is too long to fit. I mean, if I want to put a new line in Python, but I can't put a new line, this basically nullifies a new line. So it's like one long string here, but it wouldn't all fit in the slides, so I put a backslash. That way you can just copy and paste this code, and it will actually run, and you can see what it gives you. You have to add it to the 2016 though, to the URL. Okay. Any more questions? Yeah. Mm-hmm.
The second find, we don't have an ID attribute mentioned within the font.
Correct.
So what is the difference? I'm also seeing a find all function there.
Sorry, say that last thing again?
There's also a find all.
Yeah. Yeah, so again, okay, so the question was, there's two questions. One was, this has an ID, these ones don't have IDs, and then what's the deal with this find all thing? Okay, I'll answer both of those. But again, the bigger point here is that if you want to sort of, and then we'll cover this a little more next time actually, but if you want to sort of figure out what a call is doing, the best way to do it is actually just to look up the documentation for that call. I'll say in this case. So you're absolutely right. What this means is that essentially, just like in our past example, there was an attribute on this first one, but not on this subtag. What that means is that there's an attribute that says ID equals schedule for this tag here, but there are no attributes that we care about, at least, or that we're going to use to down select in these ones. Now, in terms of the find and find all, find will return the first instance of the tag that it finds in the document, and then go from there, return that as a single object. And then find all will return a list of all the objects it finds. So this returns all the A objects, and A is HTML for a link, and so it will return all the links that occur within that table body as a list. So that's what it is. But again, sort of the fun part here is being able to see code like this and then finding the docs that sort of describe it, or figure out what call you want to do without anyone even showing it to you. Okay, so let's move on to the one thing that I think actually has a little bit of technical depth, maybe, in this lecture at least, which are regular expressions and some amount of parsing, though actually I'm going to basically just focus on regular expressions here, I think, from time. Okay, so regular expressions are sort of an invaluable way of matching text within a document. Right? So once you've loaded data, or say I want to build a new parser for some new format I haven't, where I understand the format, but I don't have a parser for it. One very common thing you're going to want to do is you're going to want to search for elements within the data. Right? And this actually applies really no matter what kind of data you're analyzing. So even if you're looking at CSV files, you'll probably do some amount of regular expressions to analyze your CSV file on some level. It's very, very common to sort of do that kind of stuff. So the first, and I think that regular expressions are sort of best taught just by example. So I'm just going to kind of jump in and tell you about the main function calls here and what regular expressions look like in practice. Okay? So say we have some text called, says this course will introduce the basics of data science. We import the RE library for regular expressions, and we call things like re.search, R data science in quotes, or this R, I'll talk about it in a second, but it is frequently used for regular expressions. We'll talk about what it means in just one second. And we search for it in the text itself. And what this does is that this searches for the first occurrence of the term data science within the text. And it returns an object called match. And match will have actually a few different parameters. One parameter is the start of the match. And that actually start will be 49 here, meaning that the word data science here occurs in the 49th position of that string. So nothing too impressive here so far. But if I want to search for something, I just enter the string that I search for. It'll search the string for the occurrence of that, and then it'll kind of go from there. You'll get back information about where that match was found. Okay, now there's a few different calls to regular expressions that are worth remembering, at least, and again, these are the kind of things that I even look up sometimes to remind myself which one does which. So don't worry if this is a little bit, if you don't remember these particular ones. But there are essentially, basically, 3 or 4 functions you'll actually use. Maybe one more when you talk about substitutions, but 3 or 4 functions you'll use to find text using a regular expression. All right, and the first one is called re.match. That will search for a match of that string, of that text to that string, to the regular expression, just at the start of the text. All right, so actually if you run here re.match data science on this text, it would return none. It would return an empty, the none object, because the beginning of the string does not match this regular expression here. .search will search through the entire string to find it and return where it was found in that string, if it found it. Then find iter will return an iterator over all matches. So search will just find the first one. Find iter will return all of them. And then find all will return also all of them as a list rather than as an iterator that you loop over. So those are the main calls you will use to sort of iterate over the searches or find expressions using a regular expression in some text. Yeah?
What's the use of the first one, I.match? Because if you're specifying the text in the command, you know that the text is starting with that particular string. That is
Right. So the use of a regular expression that has just text in it is actually very uncommon. I'm using it as a first example. If it was just searching for exact strings, it wouldn't be very useful. The real advantage of regular expressions is what you can do in addition to that. So you can do some very complex sort of things that involve matching, which we'll talk about in a second. And you can also do things like, you could do things like, for example, iterate over every line in a text field and see, or in a file, and see which ones start with data science, which ones actually match that regular expression. Just know that match always means match from the beginning of the string, not just find it somewhere in the string. And that's actually a very common, I'm pointing it out because it's a very common mistake. People say .match and they clearly has that string somewhere in the text that doesn't return anything, and it's sort of very confusing. So just know that match is match at the start of the string, search is search throughout the whole string.
What's the start, like the first?
First character of the text. So it would be this course will, right? Text is equal to that thing. So it's the start of that string. Yeah?
What's the use of find iter if find all returns a list that you can also like iterate over?
Yeah. Okay, so the question was, what's the use of find iter if find all you can also iterate over? So in general, actually, there's two things. First of all, in Python, you typically want to use iterators instead of lists anyway. But actually, more than that, find all does not return this is actually an annoyance, I think, of the library, but find all does not return a list of match objects. It just returns a list of the actual strings that were matched to it. So it's much less useful because you can't really get much information about where the matches occurred. So you typically want to use find iter instead of find all, actually. So that's why I said there's 3 or 4. This one's kind of nice for thing about how many matches there are, for example, but I typically will use find iter to get actual information about each match. And you can actually do other things like that too. So you actually can set a match with a different start position, not just 0. You can specify that. And there are various other things you can do. You can also actually compile a regular expression. And that makes it a slightly more efficient form to search for. So you can actually compile this expression here and then apply it to text, do a search on text, find iter on text, etc. Right? So those all also work. Okay, so now this is sort of great, but like it was mentioned already, what's really the use of just being able to find strings? I mean, it's great we can do that, but it doesn't seem all that useful, right? So the real power of regular expressions is that you can actually come to the ability to match multiple possible sequences of characters. So there are a bunch of special characters, and these special characters are used to do things. So if you want to match one of those exactly, you actually have to escape it first. So if I want to match the $, I say \$. But here are some of the more common rules for matching characters here. Right? So if I want to match the character A, I just type A. That's sort of what we saw before. Right? Data science matches the string data science. But if I want to match the character A, B, or C, so I want to, and I'll have a few examples in a second. But if I want to match this, I have some string that where the first character is either A, B, or C, and any of those should match my regular expression. I put A, B, C inside of square brackets, and that means any of those characters. If I want to say any character except A, B, or C, I put a little caret inside the bracket there. Right, so this would actually match any character except A, B, or C. I can match any digit. For example, with the special escaped string \D. That will match any digit between 0 and 9. It also is smart. So if I say like A to Z, A dash Z, it will know I mean any character between A and Z. I can simply say any character 0 to 9. It will know that means any numeric character. But I can also just write \D. That will match any digit. I can match any alphanumeric character. Like if I say, for example, A to Z, big A, that should be a big Z, 0 to 9, or say an underscore. That's a sort of a common way of indicating variable names and stuff like this. I guess you can't actually start with this would be any of the ones, including digits or alphanumeric strings or an underscore. That the simple word for that is \w. \s matches white space, a space, a tab, a new line, a return, a feed. I don't even know what \v is. It's some sort of white space character. And then, of course, you can match any character, and that's sort of a useful thing. With just a dot, will match actually any character at all. So that's the code for match anything. By default, regular expressions were always sort of applied line by line to files. So the default behavior actually is that this will not match a new line. You sort of match things line by line. But you can make it match new lines if you include the re.all parameter in the call to the regular expression. And these are actually, so this is, I think, actually the extent of the things that and I include them here because they're the things that I actually remember about regular expressions that I actually typically use in practice. There are a million, and I guess, and the next one, but in terms of actually specifying sets of characters, this is the ones I actually use in practice. There are a lot of other ones, and again, the way to find that is the documentation on regular expressions, but these are the sort of sequence of characters that I actually remember. Okay, so the other thing you can do, though, is match multiple occurrences of a character. So you can match one or more instances of the character or the set of characters. So for example, if I want to match A exactly once, again, I just say A before. Right? So that was just, data science really was kind of code for match D once, match A exactly A once, match exactly T once, match exactly A once, etc. But you can have a modifier after those characters to match them multiple numbers of times. So for example, if I say A question mark, that will match an A 0 or 1 times. So it could be there, or it couldn't be there. It's like an optional A. So if I had I'm just going to set up this thing next time, but I won't write it. I'll just say it this time. If I had like a DA question mark TA for data, that will match both data or it would match DTA, the strings, right? So the second A would be optional in that case. I can have a star which matches 0 or more times the character, so it could be DA or DAA or DAAA, how many times ever you wanted it, or none at all. 1 or more times is a plus, and match exactly n times is brackets after the term with the number of times you want to match it. Okay, so now we have sort of given you the basic rules. Let's start actually looking at some examples. This is where we'll have our first class poll in a second. So for example, if I want to match something science, the string something science here, one way of doing that would be \w plus. That means some alphanumeric string, some alphanumeric character repeated 1 or more times. Right, so there has to be 1 or more times. It can't be no times. But 1 or more times, so something that involves A to Z, capitals, 0 to 9, and then possibly the underscore. Space, so any kind of white space here. 1 or more of them again. You could have several spaces or just one space. That could also be a new line, things like this. And then the actual term science. Okay. All right, so let's come up with a slightly more interesting example. Not very much more. But let's think about this term. The expression I gave you before. Tell me if it will match these different expressions. Okay, so this is our first in-class poll. So I admit here this is going to be a test, and if you can't submit this one on Piazza, don't worry. This will, from now on, it will be actually a measure of class participation, but today it'll be kind of a fun test you can all do. Okay, so let's go to, let's see. Okay, let's go to this poll. Let me close this. All right, and so our poll here says on Piazza, I'm going to actually bring it over here. All right, let me bring over my poll here. And it says, what strings will be matched? Oh, actually, shoot, I had the wrong thing there. I didn't add that in my slide somehow. There's actually supposed to be a capital S and an S in brackets there in the slide. Let me fix that really fast. Okay, that's a better thing. Okay, so this is a regular expression, and I want to say if I call re.match, which of these will it match? Okay, and so I'm going to go over to Piazza now, and I'm going to open the poll. So, oh wait, where did my window go? There we go. Okay, I'm going to open the poll, and so now you should be able to vote in this poll. The first one I think everyone pretty much got. I had just talked about that, so that's good that we got it. The only different thing was that the science was capitalized, right? So but I allowed for capital and a capital S or a normal S in my characters there. So the first one, which is life science with a capital letter, life obviously is a alphanumeric string, so it's one or more alphanumeric characters, and science is a capital S followed by C-I-E-N-C-E. The second one was split, which I didn't actually define this is actually fine that it's split because it's basically a random chance whether you got it or not. The question is, does a match care about what's after the string or not, right? And actually, it will match that one. So you can have stuff after a string and it will still match it. That's considered a match. So actually, it will match. But again, I didn't tell anyone that, so that's more did you, again, I think it was actually exactly a coin flip whether people thought you could go on or afterwards. So again, important point here is to vote, not to vote correctly. Life.science. So who would someone actually care to say why they think it would match that? Or wouldn't, I guess. Any volunteers? Yeah. Exactly. So the answer. So what he said was that it would not match that because the dot is not an alphanumeric character. My regular expression just has alphanumeric characters one or more, then spaces one or more. So the dot doesn't appear anywhere there, and therefore it wouldn't match that thing. So anything that sort of falls outside the scope of the regular expression will cause the whole thing not to be matched. And what about the last one? Does anyone want to venture a guess there? So the question was only, actually, okay, so sorry, so you were saying it would match it?
No.
It would not match it. Why wouldn't it match it?
There's only one space, one space, science.
Yeah, so I mean, I think the answer is that there could only be one, you have to have all alphanumeric characters, then one or more spaces, then this word science. And space is not an alphanumeric character, so you can't somehow bunch this data into alphanumeric followed by space, right? It has to be space and alphanumeric than that. Now, it would match it if you use the re.search, because then that would be finding data, something science anywhere in it. But because we're talking about match here, it will only match the beginning of it, and so this data does not apply to an alphanumeric. It would not match that regular expression there. Okay, so hopefully that gives some sense of these things. These are very simple examples. They get very nasty very quickly, which I'll show some hints of that in a second. And those working on the, let's see. Those working on, there we go. The 68 homework of writing an XML parser will have a lot of fun using regular expressions within their XML parser. Okay, also a show of hands, who was not able to submit the poll? Okay, that is, did you not, okay, so of those, did you have a computer and have a Piazza account? So who had a computer and a Piazza account and still couldn't submit the poll? Okay, so there's some debugging to do. If you were in that boat, today don't worry about it. I will open up the poll after class again so you can vote and see that you can vote and make sure that you're able to vote. It could just be your internet not working or something like that, or it could be some other fundamental problem. After today, from then on, if you can't vote for any reason, either you're not here or it doesn't work, fill out the quiz afterwards just to cover your bases. Because the voting is how we gauge who's here and who's not. Hopefully also, now that you know it's coming, it'll be a little bit faster. And just try voting really fast next time maybe. Or when I'm moving my cursor to close the poll, just vote anything, and that's the secret, right? Okay, so a couple last things. A very sort of important point of regular questions is this notion of what's called grouping. So oftentimes I want to match some expression, but I want to also save the results of what I matched there. Okay, so for example, if I have this string, data science here, I guess I only allow one space there. But if I had this string, I'm matching data science, I might want to remember what's the first thing that I matched here. Like, what is the string that I matched at the beginning here? And you could do that by finding where the start was and then extracting kind of the text of this string. But there's an easier way to do this with regular expressions, and that is something called grouping. So if you have any portion of your string or your regular expression that you want to remember, you enclose it in parentheses. And when you do that, you find your match, and there's also something called match.groups. So it returns both where the match was. So in our thing here, we have text that we're using from long ago, which just had the string data science somewhere in it. It says the match happened at character 49. But the groups indicate what you actually matched to. So the group here is a tuple that says data and science, meaning the first thing, I didn't know what that was when I matched it. The first thing that I matched there, this string, was in fact the word data. And this string, it could have been science capitalized or uncapitalized. It was actually the uncapitalized version in that string. Right? So this lets you kind of figure out what you actually matched to, which will be very important, for example, in your XML parser. You'll want to find, you'll want to essentially parse for tags in XML. And it'll be very good to know what that tag actually is that you just detected, that you just matched. Now, one other brief point, and I put it here. I don't know if it's really goes here, but I should just sort of make this point. Why do we have the R there in front of these things? The reason for that is that by default, Python strings, that is strings that have double quotes or single quotes, if you have a character like \n, it will actually imply a new line in the string. But in regular expressions, you actually want to indicate that \n is actually matching a new line, right? So you want to encode the characters \n. So having the R there means it won't escape backslashes essentially. So the backslashes end up in the actual string, and that's much, much easier. Otherwise, you have to get into really sort of nasty remembering how many times to add backslashes to get the regular expression you want out of the text string that you want. So just use R there always as a habit. It just makes things much, much easier in practice. Okay, so the last thing that I'll add is substitutions. So this is actually a very useful tool that we have. And I use it a lot, for example, in the converter that I use to post notes, which actually takes them from a Jupyter Notebook to markup language or for Markdown for the website. I use substitutions a lot in that. So what these do is these actually let you take a text and have two regular expressions and replace the first one with the second one. So I can take all occurrences of actually whether or not you do it many times or once. By default, I believe sub here does many times, but other ones just do once. Here, I think it does many times. What this will do is it'll take all occurrences of data science in text and replace it with sort of schmata science here. And of course, that's again useful, but you could do that kind of manually with a number of techniques. What's really useful about regular expressions and substitutions is that I can actually use groups within substitutions to do very powerful manipulations of text. Right? So if I want to take any term that says anything science, that can be capitalized or not. I can replace that, so life science would match this, life capital science would match this, etc. what would actually this expression do? Does anyone know what it will do? What it will replace it with? Yeah.
It'll replace it with like the character space Schmeins.
Yes. So the answer is it replaces it with the first word here, space Schmeins. So data Schmeins basically here is what it replaces it with. But the way this works is that look at what's being matched in the groups here. So the first group contains the alphanumeric string that happens before the science term. And the second match happens with the term here, capitalized or not capitalized, the first term in science, right? And what's nice about this is this, and this notation here, this \1 replaces the first group match. So it will replace the string with whatever was here. And this one will replace the string with whatever is here. So the nice thing here is this will preserve, for example, capitalization of your, data Schmeins term. If I capitalize science, it would be capitalized here. If I didn't capitalize science, it wouldn't be capitalized here. Now, this is a really powerful set of sort of tools that you have here, right? Because it lets us actually take pretty complex expressions, find certain subgroups within those expressions, and automatically replace it with something else. So as an example of what I do, and I might release this code at some point or not, I don't know, but I have my notes that I'm writing for the course are written in Jupyter Notebook. And there's a certain way of displaying an image in Jupyter Notebook that is not the same as what I want to do on the actual website. So I have a substitution string that looks for essentially images in the Jupyter Notebook, or the notation for images in the Jupyter Notebook, and replaces it with ones that work in Markdown, while keeping the link to the URL and like the subtitle of the image and all that kind of stuff. So you can do really powerful transformations with these routines here, and they will sort of be key to writing your XML parser. I guess you don't have to do so much substitutions, just matching, but these sort of tools in general of regular expressions are extremely powerful. Now, one thing I will say is that if you think, which is not important, this is kind of an aside, but actually it turns out that regular expressions can't, while they are very powerful, kind of basic regular expressions from a true sort of programming standpoint can't capture everything. For example, they can't capture languages like XML that have open and close brackets. You actually can't sort of match an opening one here and match that same thing over there. Now you can do it, but you can't always do it. But that's sort of what I'll say. You can do it with non-regular expression extensions to regular expressions that they have in Python. Okay. I'm out of time here. I'll say one more thing about order of operations. If you have something like this, which is A, B, C, or D, E, F, that matches one of those two strings, not A, B, C, D, or F. So there is an order of operations to these things. So you have to just sort of learn. The last thing I'll say, and you can kind of use the various groups to capture. So you can basically do this with, you can force order of expressions by having parentheses, but parentheses also imply groups. So if you don't want groups, you add this little question mark colon here. And this is why these things get so ugly so quickly. Also a very important thing about greedy matching, by default, if I have this regular expression and applied to a text like this, it will match the entire thing because there's a opening paren, there's some other stuff, and a closed paren. So it won't match this part here. It'll match as much as it can, so it'll match the entire string. This will be very important in your XML parser. If you want to just match this first string, use something called lazy matching, which is this term here with a question mark after it, and that will only then match the first string there. Okay, so that's actually all we have for today. You will use this a lot, I promise. The other big thing is, though, don't worry if you don't remember this notation. Just like library documentation, you will have to look it up, and that is fine.